in a linear scenario, if there's more than one line, so 2 or 3 or 4 or however many, when we're comparing two of those lines, one of a couple things is going to happen, one of three things actually. And so when we look at a linear line, there's basically some information that we need to know. Just as review, we look at a line. It goes on forever. It has a domain of negative infinity to infinity, as well as a range from negative infinity to infinity. Most of the time, it's represented by the line y equals mx plus b, where m is the slope and b is the y-intercept. And so those are the two critical things that we kind of got to know and make sure we bring that back into play. Now, the scenario starts happening when we look at two lines that are graphed on the same grid. And so there's something unique that starts happening. This point right here is called a solution, and that solution is when the lines are the same. So a solution is when the two lines that we're comparing are equal. This happens in most scenarios with the intersection of linear lines. And so when lines cross, this is what happens. So I want to show you kind of the different things here that could exist inside of a linear scenario with more than one line. So looking at this grid, I see that we have two lines graphed, a red one and a blue one, and that solution point right there is actually the really important piece, and that's when this line, we'll just say y1 or function 1 and function 2 are equivalent. And so those two lines are the same at that point, and it looks like it is at the point negative 3. So that is the solution point of this. Now that solution point, like I said, tells us when the lines are the same, but that's when it happens. And so we can look at these two lines here, and this happens a lot, but sometimes there's a very unique solution point or something unique that happens at the solution point. So again, here's the scenario. We have a red line and a blue line, and there is one solution, and so we're noticing that there's only one time it intersects. And that one solution happens right, let's get off of that, go black, right there. So, but something unique's happening at that point, and it's really kind of hard to tell just from the graph, but as we write the equations, something unique starts happening. So this is inside of one solution, there's a special case, and we get y equals, and I'll tell you go ahead and tell you the equation of this red line is y equals 2x plus 3. The equation of the blue line is represented by y equals negative 1/2 x plus 3. So obviously our solution point is that y-intercept. We see it be the same in both problems. And so we know our solution is 0, 3. But something more unique in this is you kind of see a special relationship start happening with the slopes. The slopes are what we call negative reciprocals. And those negative reciprocals, and I'll write that down for you, that negative reciprocals, and that means opposite flip. And so here's kind of the scenario that would happen. If we had 2 as our slope, then the negative reciprocal of that would be negative 1/2, because that 2 has a denominator of 1. And so another way of writing it would be that if m is over n, then the negative reciprocal of that is equal to negative n over m. And so really pay attention there. If you start seeing that relationship, this creates a perpendicular line. And so this actually isn't as critical anymore. So having one solution is still important, but more important, it is perpendicular. Spelling. So these two lines are perpendicular to one another. And what that means is that they intersect at a right angle. And so these are actually right angles in here. So it's really hard to tell from the graph because of the way that the lines are squished together based on the scale. But if the slope relationship between 2x and negative 1/2x is that negative reciprocal, we know that these are perpendicular lines. So if they're negative reciprocals or opposite flips of each other, that's what makes it perpendicular. So the next type of solution I want you to see is one that's really hard to see in the graph because one line covers up the other. And so I see two lines here. Those two lines that are happening just happen to be the exact same over here. So there should be a red line, but I don't see it because of the blue. And so this is an infinite set or infinite solutions. And that means that these lines are exactly the same. And so these lines will always be on top of each other, and they will always intersect because they are the same line. So really there's two lines in there. One is red, and the other is on top of that, and it's blue. And as those lines have the exact same slope and the exact same y-intercept, that means those lines are exactly the same. That tells us that they are infinite. Clean that up a little bit. They are infinite. They are infinitely connected. Infinite solutions. Pretty easy that you have to have the same slope and the same y-intercept. Once those two are the exact same, you know it's the same line in an infinite set. So the last scenario of two linear lines that we're going to look at is this one. And this one is actually a parallel set. And so these two lines run infinitely next to each other, like railroad tracks. This produces no solutions. And there's something unique happening here as well. Let's say that this line is still y equals 2x plus 3. The blue line is also y equals 2x, but something's different. It looks like it's minus 3. And so that difference that happens in that y-intercept causes the lines to run exactly at the same rate of change, but one above and one below each other. And so that creates no solutions. Those lines are parallel. And so if the m's are equivalent, but the b's are different, then you have a parallel set, and those are never going to touch, and therefore produce no solutions. Remember, a solution is when the two lines cross. So these lines will never cross because their slopes are the same, but their y-intercepts are different. So to quickly review, when looking at linear lines, so two or more linear lines, there's one of three things that can happen. Either, and the most common is there is a solution where the lines cross. Where those lines cross, that's the important information. So that's the solution. Inside of one solution, there's a significant thing that happens, and that happens when lines are perpendicular to one another, producing a 90-degree angle between them. That happens when the slopes are opposite flips or negative reciprocals. Those words mean the same. So if m is over n, then the negative reciprocal of that is negative n over m. Again, that's with slope. When the slopes are that way, the y-intercept does not matter, just slopes. Another scenario that happens when we're dealing with two or more linear lines is that they're the same line. And when they're the same line, both y-intercept and slope are the same. This produces infinite solutions. They're always going to touch, they're always going to intersect, they're always going to be the same. The last scenario that happens when looking at linear lines is that they're parallel. And those parallel lines will never cross. So this will produce no solutions. And the m's are the same. M1 of whatever line has to be equal to M2 of the opposite line. Now the b's, however, are different. b1 does not equal b2. So the y-intercept on the on the red line doesn't equal the y-intercept on the blue line. If they were, if the both were the same, it would be here. And so going back to the same line, m1 is equal to m2, and b1 is equal to b2. And so if both of those things are true, then you have the same line in infinite solutions. If only the slopes are the same, but the y-intercepts are different, then you have no solutions, and those lines are parallel. That would be parallel. So hopefully this helps. Hopefully this makes some sense. There's one of three things that can happen. There's a special case inside of a solution. Make these notes. Make sure you identify which m and which b need to be the same and which need to be different. And we'll start looking a little bit more at when we graph or have a scenario with more than one linear line.